Tonight, we're visiting the coldest place in the known universe, not Antarctica, not deep space, but a location so cold it's 1 degree above absolute zero, colder than the cosmic background radiation itself. This place exists right now, 5,000 light-years away, created by a dying star that's cooling itself through pure thermodynamics. Understanding why this nebula is so cold will teach you about stellar death, the laws of physics, and the ultimate fate of everything. If exploring extreme temperatures sounds fascinating, a quick subscribe would mean the world to me. Let's begin. Before we can understand the coldest place in the universe, we need to understand what cold actually is. Most people think of cold as a thing, as if coldness is a substance that can flow into objects and make them cold. But that's not how physics works. Cold isn't a thing at all. Cold is the absence of heat. Heat is energy. Specifically, heat is the kinetic energy of molecules moving around. When something is hot, its molecules are moving quickly, vibrating rapidly, bouncing off each other with lots of energy. When something is cold, its molecules are moving slowly. They have less kinetic energy. And when something approaches absolute zero, the coldest possible temperature, its molecules are moving as slowly as the laws of physics allow. Temperature is a measure of average molecular kinetic energy. On Earth, we usually measure temperature in degrees Celsius or Fahrenheit. Water freezes at 0 degrees Celsius, which is 32 degrees Fahrenheit. Water boils at 100 degrees Celsius, which is 212 degrees Fahrenheit. These scales are based on water because water is important to human life. But scientists use a different scale for measuring extreme temperatures. The Kelvin scale starts at absolute zero, the coldest possible temperature, and goes up from there. Absolute zero is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. At absolute zero, molecular motion doesn't stop completely, but it reaches its minimum possible value allowed by quantum mechanics. Here's something important to understand. You can't actually reach absolute zero. It's physically impossible. The third law of thermodynamics states that you can approach absolute zero but never quite get there. The closer you get, the harder it becomes to remove more heat. It would take infinite energy and infinite time to cool something to exactly absolute zero. This isn't a technological limitation we might overcome someday. It's a fundamental law of nature, as unbreakable as the speed of light being the cosmic speed limit. But we can get very close, and nature, in certain extreme circumstances, gets closer than you might think possible. On Earth, the coldest natural temperature ever recorded was minus 89.2 degrees Celsius at Vostok Station in Antarctica. That's about 184 Kelvin. It's incredibly cold by human standards, cold enough to instantly freeze exposed skin, cold enough that your breath would crystallize and fall as ice particles. But on the cosmic scale, 184 Kelvin is actually quite warm. Room temperature is about 293 Kelvin. So Antarctica's coldest temperature is only about 100 Kelvin colder than a comfortable room. That might sound like a lot, but we're going to be talking about temperatures hundreds of degrees colder than that. In space, things get much colder. The average temperature of the universe itself is about 2.73 Kelvin. This is the temperature of the cosmic microwave background radiation, the leftover heat from the Big Bang. Everywhere you look in space, in every direction, there's this faint microwave radiation with a temperature of 2.73 Kelvin. It's the echo of the universe's birth, cooled down over 13.8 billion years of cosmic expansion. Any object sitting in empty space, far from any stars, will eventually cool to about this temperature. The object radiates away its heat into space, and it absorbs this background radiation, reaching equilibrium at 2.73 Kelvin. But the coldest place we've found isn't sitting passively in space. It's actively cooling itself through a process so efficient that it reaches temperatures below the cosmic background radiation. This place is called the Boomerang Nebula, and its temperature is about 1 Kelvin. That's 1 degree above absolute zero. It's colder than the background radiation of the universe itself. It's colder than anywhere else we've ever observed in nature. And it's achieved this temperature through a dying star's final act. The Boomerang Nebula is what astronomers call a planetary nebula, though it has nothing to do with planets. Planetary nebulae got their name because early astronomers looking through telescopes thought they looked like the disks of planets. They're actually shells of gas expelled by dying stars. When a star similar to our Sun runs out of hydrogen fuel in its core, it begins to die. The core contracts and heats up while the outer layers expand. The star becomes a red giant, swelling to many times its original size. Eventually, the outer layers become so loosely bound that they drift away into space. The star sheds its outer envelope, creating an expanding shell of gas. This shell is a planetary nebula. At the center is the star's exposed core, a white dwarf, incredibly hot and dense. The Boomerang Nebula is about 5,000 light-years away from Earth in the constellation Centaurus. It was discovered in 1980 when astronomers surveying the sky in infrared light noticed something unusual. The nebula appeared extremely cold. Follow-up observations in the 1990s using radio telescopes confirmed that the Boomerang Nebula was indeed extraordinarily cold. Measurements showed a temperature of about 1 Kelvin, possibly even lower in some regions. This made it the coldest known natural place in the universe, a record it still holds today. What makes the Boomerang Nebula so special? Why is it colder than the cosmic background radiation, colder than empty space, colder than anywhere else? The answer is expansion. The star at the center of the Boomerang Nebula is expelling gas at an incredibly high rate. Estimates suggest it's blowing out about 1,000th of a solar mass per year, which is about 100 times faster than typical dying stars. This gas is moving outward at speeds of about 170 kilometers per second. That's incredibly fast, over 600,000 kilometers per hour. And this rapid expansion is what creates the extreme cold. To understand why expansion causes cooling, we need to talk about thermodynamics. When a gas expands, it does work against its surroundings. It pushes outward, and pushing requires energy. This energy comes from the gas's internal thermal energy, its heat. As the gas expands and does work, it loses thermal energy and cools down. This is the same principle that makes refrigerators work. A refrigerator uses a compressor to compress and expand a refrigerant gas. When the gas expands on the inside of the refrigerator, it cools, absorbing heat from the food inside. The gas then gets compressed outside the refrigerator, releasing that heat. The Boomerang Nebula is essentially doing the expansion part of this cycle, but without the compression part. It's just expanding forever, cooling as it goes. The rate of cooling depends on how fast the expansion happens. The faster the gas expands, the more work it does, the more it cools. The Boomerang Nebula is expanding so rapidly that the gas cools faster than it can absorb heat from the cosmic background radiation. Remember, space itself has a temperature of 2.73 Kelvin due to the background radiation. Normally, an object in space cools until it reaches this temperature, then stops cooling, because it's in equilibrium with its surroundings. But the Boomerang Nebula's gas is expanding so fast that it overshoots this equilibrium. It cools below 2.73 Kelvin and keeps cooling as it continues to expand. Think of it this way. Imagine you're in a room at 20 degrees Celsius and you start running a fan that blows air outward from the center. If the fan is powerful enough, the air near the fan can become colder than the room temperature because the expansion of the air cools it faster than the room can heat it back up. The Boomerang Nebula is like an incredibly powerful fan in the cosmos, blowing gas out so fast that it becomes colder than the universe around it. But there's more to the story. The shape of the Boomerang Nebula is also unusual. High-resolution images from the Hubble Space Telescope show that it's not a simple spherical shell like many planetary nebulae. Instead, it has a distinctive hourglass or boomerang shape, which is how it got its name. There are two main lobes of gas extending in opposite directions from the central star, with a denser waste region between them. This shape suggests that the gas isn't expanding uniformly in all directions. Something is channeling the outflow into these specific lobes. Many astronomers think the dying star might have a companion, another star orbiting close by. The gravitational influence of this companion could shape the gas outflow, creating the observed structure. The extremely cold temperature is concentrated in the densest parts of the nebula, the regions where the gas is expanding most rapidly. As the gas moves farther from the star and becomes more diffuse, it starts to warm up slightly by absorbing background radiation and starlight from the galaxy. But in the dense, rapidly expanding inner regions, the temperature stays at about 1 Kelvin. This is cold in a way that's hard to comprehend. At 1 Kelvin, molecules move incredibly slowly. The kinetic energy is so low that even normally gaseous substances would freeze solid if they were at this temperature in the right conditions. To put this in perspective, let's think about what happens to different substances at these extreme temperatures. Hydrogen, the most common element in the universe, becomes a liquid at 20 Kelvin under normal pressure. Below 14 Kelvin, it freezes into a solid. Helium, which is normally very difficult to liquefy because it's so light and its atoms interact so weakly, becomes a liquid at about 4 Kelvin. At 1 Kelvin, even helium can exhibit strange quantum behaviors. It becomes a superfluid, a state of matter with zero viscosity that can flow without friction. The Boomerang Nebula is cold enough that if there were a pool of liquid helium sitting in it, that helium would be a superfluid. Now, the gas in the Boomerang Nebula isn't pure hydrogen or helium. It's a mix of elements, mostly hydrogen and helium, but with heavier elements like carbon, nitrogen, and oxygen mixed in. These heavier elements were created in the star's interior through nuclear fusion during its lifetime and are now being expelled as the star dies. At 1 Kelvin, many of the molecules in the nebula would condense into ice particles if the density were high enough. But the nebula is also extremely diffuse. It's a better vacuum than anything we can create on Earth. So even though it's incredibly cold, there isn't enough density for most substances to condense. The molecules are too far apart to stick together. How do we know the Boomerang Nebula is this cold? We can't stick a thermometer in it. It's 5,000 light years away. We measure its temperature using spectroscopy and radio astronomy. When molecules in space absorb or emit radiation, they do so at specific wavelengths that depend on their energy states. By observing which wavelengths are present or absent in the light coming from the nebula, we can determine what molecules are there and how much energy they have. From the energy, we can calculate the temperature. One particularly useful molecule for measuring cold temperatures is carbon monoxide. Carbon monoxide emits radio waves at specific frequencies that depend on its rotational energy. In a gas, molecules rotate, and the speed of rotation depends on temperature. By measuring the intensity of different rotational transition lines of carbon monoxide, astronomers can determine the temperature of the gas very precisely. In the Boomerang Nebula, carbon monoxide measurements showed that the gas was at about 1 Kelvin, much colder than expected. This discovery was surprising and exciting because it revealed that nature could create temperatures lower than the cosmic background radiation, something that wasn't widely appreciated before. The Boomerang Nebula isn't the only cold place in space, though it is the coldest we've found so far. Dark nebulae, dense clouds of gas and dust that block background starlight, can also be very cold. These clouds are the birthplaces of stars. They're regions where gas and dust have accumulated to high densities. The dust blocks starlight, preventing the cloud from being heated. The gas cools by radiating infrared light into space. Some of these clouds can reach temperatures as low as 10 Kelvin. This is still much warmer than the Boomerang Nebula, but it's cold enough for many molecules to freeze onto dust grains, creating ices of water, carbon monoxide, methane, and other substances. These ices are important for chemistry in space. They provide surfaces where molecules can meet and react, forming more complex compounds that might eventually become part of planets or even life. The space between galaxies, the intergalactic voids, are also very cold. In these vast empty regions, there are very few stars and very little gas. Without stars to provide heat, the only significant source of energy is the cosmic shunk's background radiation, so the temperature in these voids is close to 2.73 Kelvin. There's essentially nothing there, just a few atoms per cubic meter, and the faint glow of the Big Bang's afterglow. These regions are cold and empty and dark, as close to nothingness as the universe gets. But even these voids aren't as cold as the Boomerang Nebula. That's what makes the Boomerang Nebula special. It's actively cooling itself through expansion, pushing below the background temperature that pervades all of space. It's the champion of cold, the coldest natural place we've ever found in the entire observable universe. Let's compare this cosmic cold to the cold we experience on Earth. The coldest temperature ever recorded on Earth, as I mentioned, was minus 89.2 degrees Celsius in Antarctica. This happened at Vostok Station in July 1983 during the Antarctic winter. At this temperature, carbon dioxide freezes. The air itself begins to condense. It's lethally cold. Exposed skin would freeze in seconds. Breathing this air would freeze your lungs. But in Kelvin, this is 184 degrees above absolute zero. It's cold, but it's nowhere near the extremes we're discussing. In laboratories, scientists can create much colder temperatures than nature provides on Earth. Liquid nitrogen, commonly used for cooling in labs, has a temperature of 77 Kelvin. This is the temperature at which nitrogen liquefies under normal atmospheric pressure. Liquid nitrogen is very cold. If you pour it on the ground, it boils violently, turning from liquid back to gas. If you put a flour in it, the flour freezes solid instantly and becomes so brittle it shatters like glass. Liquid nitrogen is used for preserving biological samples, cooling superconducting magnets, and even making ice cream in fancy restaurants. Liquid helium is even colder. Helium liquefies at about 4 Kelvin, and if you reduce the pressure, you can cool it further to below 2 Kelvin. Liquid helium is strange stuff. At temperatures below 2.17 Kelvin, it becomes a superfluid, a state of matter with bizarre properties. A superfluid has zero viscosity. It flows without any friction. If you put a superfluid in a container, it will creep up the walls and flow out over the edge. It can flow through impossibly tiny cracks. It's one of the most counterintuitive substances in physics, and it only exists at temperatures within a few degrees of absolute zero. But scientists have pushed far beyond liquid helium. Using advanced cooling techniques like laser cooling and evaporative cooling, researchers have reached temperatures of a few billionths of a Kelvin. That's nanokelvin, a tiny fraction of a degree above absolute zero. At these temperatures, atoms move so slowly that quantum mechanical effects dominate. Atoms behave more like waves than particles. They can overlap and synchronize their quantum states, forming something called a Bose-Einstein condensate, a new state of matter that doesn't exist at higher temperatures. This is physics at its most extreme and most strange. So we have a range of temperatures. Room temperature is about 300 Kelvin. Antarctica gets down to about 180 Kelvin. Liquid nitrogen is 77 Kelvin. Liquid helium is 4 Kelvin. The cosmic background radiation is 2.73 Kelvin. The Boomerang Nebula is 1 Kelvin. And in laboratories, we can reach billionths of a Kelvin. Each step down this scale requires more sophisticated techniques and reveals new physics. Now, let's think about what happens as we approach absolute zero. What changes? Why is absolute zero special? The answer is rooted in the laws of thermodynamics and quantum mechanics. Thermodynamics tells us that heat is the random kinetic energy of particles. As temperature decreases, this random motion decreases. At absolute zero, classical physics would say that all motion stops. Particles would be perfectly still. But quantum mechanics says this isn't quite right. Heisenberg's uncertainty principle, one of the foundational principles of quantum mechanics, states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. If particles were perfectly still at absolute zero, we would know their momentum exactly. It would be zero, and if we also knew their position precisely, we would violate the uncertainty principle. So, quantum mechanics requires that even at absolute zero, particles retain some motion. This is called zero-point energy. It's the minimum possible energy a particle can have, and it's not zero. Zero-point energy means that even at absolute zero, atoms still vibrate. Electrons still orbit atomic nuclei. Quantum fields still fluctuate. The universe is never perfectly still. This zero-point energy is tiny, but it's measurable and has real physical effects. It causes helium to remain liquid at absolute zero under normal pressure. Other substances freeze solid, but helium's atoms are so light and their interactions so weak that zero-point motion prevents them from locking into a solid structure. Only if you apply high pressure can you force helium to solidify. As you cool a substance toward absolute zero, its properties change in dramatic ways. Electrical resistance in most materials decreases. In some materials, at a critical temperature, the resistance drops to exactly zero. The material becomes a superconductor. Electric current can flow through a superconductor without any loss of energy. This has practical applications in building powerful magnets for MRI machines and particle accelerators. But it also reveals deep quantum physics. Superconductivity is a quantum phenomenon where electrons pair up and move in a coordinated way, flowing without scattering. Thermal expansion also disappears. Near absolute zero, materials contract as they cool because the atoms vibrate less and can pack more closely together. But as you approach absolute zero, this contraction slows and eventually stops because you've reached the minimum atomic spacing allowed by quantum mechanics. Heat capacity, the amount of energy needed to raise a substance's temperature, also drops dramatically near absolute zero. It becomes incredibly difficult to add heat to something that's already nearly at absolute zero because there are very few available quantum states for the energy to go into. The third law of thermodynamics states that the entropy of a perfect crystal at absolute zero is zero. Entropy is a measure of disorder. At absolute zero, a perfect crystal would be perfectly ordered, every atom in exactly the right place, no thermal vibrations, minimal quantum fluctuations. This is the most ordered state possible. The third law also implies that you cannot reach absolute zero in a finite number of steps. Each step of cooling gets you closer, but you need infinitely many steps to actually reach zero. This is a fundamental limit, not a technological one. All of this extreme physics, these strange quantum behaviors, these fundamental limits, come into play when we study the coldest places in the universe. The Boomerang Nebula at 1 Kelvin is well above absolute zero. It's not cold enough for superconductivity or Bose-Einstein condensation, but it's cold enough to slow molecular motion to a crawl. It's cold enough to challenge our intuitions about temperature, and it's cold enough to teach us about the death of stars and the thermodynamics of cosmic gas flows. The Boomerang Nebula won't stay this cold forever. As it expands, it becomes less dense. The rate of expansion slows. Eventually, the gas will spread out so much that it's no longer cooling itself rapidly. It will warm up, absorbing energy from starlight and cosmic radiation. In a few thousand years, the nebula will have warmed to temperatures closer to the cosmic background. The brief period of extreme cold will be over. The nebula will join the countless other planetary nebulae scattered throughout the galaxy, no longer exceptional, no longer the coldest place in the universe. But for now, at this moment in cosmic time, it holds the record. And studying it gives us a window into the physics of extreme cold in nature. Let's delve deeper into why the Boomerang Nebula's mechanism for achieving such extreme cold is so remarkable. The process of adiabatic expansion, which is what's happening in the Boomerang Nebula, is something we encounter in everyday life, but rarely to such extremes. When you use a spray can of compressed air to clean your keyboard, you might notice the can gets cold. This is adiabatic expansion in action. The compressed gas inside the can is at high pressure. When you press the nozzle, the gas rapidly expands into the lower pressure environment outside the can. This expansion requires energy, which comes from the gas's thermal energy. The gas cools, and so does the can, but the spray can only cool by maybe 10 or 20 degrees Celsius. The Boomerang Nebula's gas cools by hundreds of degrees. The difference is the scale and speed of the expansion. The gas in the Boomerang Nebula is expanding at 170 kilometers per second. To put this in perspective, that's about 500 times faster than the speed of sound in Earth's atmosphere. It's about 0.057% the speed of light. At these velocities, the gas is doing work at an incredible rate. It's pushing against the surrounding medium, against the pressure of space itself. And this work drains thermal energy from the gas faster than any process can replace it. Another factor is the density. In the spray can, the gas expands from high pressure to normal atmospheric pressure, a ratio of maybe 10:1. In the Boomerang Nebula, the gas is expanding from the relatively high density near the star to the near vacuum of space, a ratio of many millions to 1. This enormous expansion ratio allows the gas to cool to much lower temperatures. It's the combination of high velocity and extreme expansion ratio that makes the Boomerang Nebula's cooling so effective. There's also the question of timescale. The spray can empties in seconds. The Boomerang Nebula has been expelling gas for about 1,500 years at current estimates. This sustained rapid outflow has created a massive volume of extremely cold gas. The total mass of gas in the nebula is estimated to be about 1/10 of the mass of our Sun. That's an enormous amount of material, and it's all been cooled to 1 Kelvin or below. This makes the Boomerang Nebula not just a point source of cold, but an extended region, a vast volume of space where temperatures are lower than anywhere else we've found. Now, you might wonder whether there could be even colder places out there that we simply haven't discovered yet. It's possible. The universe is vast, and we've only surveyed a tiny fraction of it in detail. There might be other dying stars undergoing similarly rapid mass loss that could create even colder nebula. But based on our current understanding of stellar evolution and mass loss, the Boomerang Nebula represents close to the coldest that natural processes can achieve. To go colder would require even faster expansion, and there are limits to how fast a star can expel material before the process becomes unstable. Some astronomers have speculated about whether the extreme cold in the Boomerang Nebula could affect the chemistry happening there. At 1 Kelvin, chemical reactions essentially stop. Molecules don't have enough thermal energy to overcome activation barriers. They can't rearrange themselves. They're frozen in whatever configuration they happen to be in. But quantum mechanical tunneling could still allow some reactions to occur. Tunneling is a quantum effect, where particles can pass through energy barriers they couldn't classically overcome. At very low temperatures, tunneling becomes the dominant mechanism for certain reactions. The Boomerang Nebula might be a laboratory for studying ultra-cold chemistry, a regime where only quantum mechanics matters and classical chemistry completely breaks down. There's also the question of what happens to dust particles in such cold gas. Dust grains in space are typically tiny, maybe a micron or less in diameter. They're made of silicates, carbon, and ices. In the Boomerang Nebula's extreme cold, any volatile materials like water, carbon dioxide, methane, or ammonia would freeze onto these dust grains, coating them in ice. These icy grains might clump together, forming larger aggregates. Over time, given enough mass and density, these aggregates could potentially form the seeds of planets. But the Boomerang Nebula is expanding and dispersing, so this process would be cut short. The material will spread into the interstellar medium, eventually mixing with other gas and dust, perhaps someday becoming part of a new star system. The central star of the Boomerang Nebula is also worth discussing in more detail. It's currently shrouded by the dense gas and dust of the nebula itself, making it difficult to observe directly. But based on the nebula's properties, astronomers can infer things about the star. It's likely a star that was originally a few times more massive than the Sun. Over billions of years, it fused hydrogen into helium in its core. When the hydrogen ran out, the core contracted and heated up. The outer layers expanded, and the star became a red giant. Nuclear fusion began in a shell surrounding the now inert helium core. This shell-burning phase is unstable. The star pulsates, and during these pulsations it sheds mass. Eventually, the entire outer envelope is ejected, creating the nebula we see. What's left behind is the star's core, a white dwarf. White dwarfs are incredibly dense objects. A white dwarf with the mass of the Sun would be about the size of Earth. The material is compressed so tightly that a teaspoon would weigh tons. White dwarfs are supported against gravity not by nuclear fusion but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. The white dwarf is very hot when it first forms, with surface temperatures of 100,000 Kelvin or more. Over billions of years, it cools by radiating away its thermal energy. Eventually, it will become a cold, dark object called a black dwarf, though the universe isn't old enough yet for any black dwarfs to exist. In the case of the Boomerang Nebula, the white dwarf is still hot, still radiating ultraviolet light. This UV radiation excites atoms in the nebula, causing them to glow. This is how we see planetary nebulae. They shine with the fluorescent glow of gas excited by the central star's UV radiation. As the nebula expands and disperses, this glow will fade. The nebula will become invisible, and the white dwarf will continue its long, slow cooling, eventually fading from view. The story of the Boomerang Nebula is a story of endings. The star is dying. It's exhausted its fuel. It's expelled its outer layers. What remains will slowly cool and fade, and in doing so, it has created the coldest place in the known universe, a transient monument to stellar death. There's something poignant about this. The end of a star's life, the dissipation of its material into space creates this extreme physical condition. It's beautiful in its own way, a final flourish before darkness. This brings us to a broader question about temperature and the universe. We've talked about the coldest place, but what about the average temperature of the universe? We mentioned the cosmic microwave background radiation at 2.73 Kelvin. This radiation fills all of space. It's the afterglow of the Big Bang, cooled by cosmic expansion over 13.8 billion years. When the universe was young, it was incredibly hot. In the first moments after the Big Bang, temperatures were trillions of degrees. Particles moved at nearly the speed of light. Matter and energy were interchangeable. As the universe expanded, it cooled. By the time the universe was about 380,000 years old, it had cooled to about 3,000 Kelvin. At this temperature, electrons combined with protons to form neutral hydrogen atoms. The universe became transparent to light. Photons could travel freely instead of being scattered by free electrons. These photons are what we detect today as the cosmic microwave background. Over the subsequent 13.8 billion years, the expansion of the universe has stretched the wavelengths of these photons. What was once visible and infrared light is now microwave radiation, and the temperature associated with this radiation has dropped from 3,000 Kelvin to 2.73 Kelvin. It will continue to drop as the universe continues to expand. In the far future, billions of years from now, the cosmic background will be even colder, maybe 1 Kelvin, maybe less. Eventually, it will approach absolute zero, though it will never quite reach it as long as the universe keeps expanding at a finite rate. This cosmic cooling is a manifestation of the second law of thermodynamics, which states that entropy or disorder tends to increase in isolated systems. The universe as a whole is an isolated system. There's nothing outside it to exchange energy with. So, the universe's entropy is always increasing. One consequence of this is that useful energy becomes less and less available. Heat flows from hot regions to cold regions, evening out temperature differences. Stars burn their fuel and die. Galaxies slowly exhaust their gas supplies and stop forming new stars. Eventually, in the very far future, perhaps 10 to the 100 years from now, the universe will reach a state called heat death. All temperature differences will have been erased. Everything will be at the same cold temperature, just a tiny fraction above absolute zero. No energy will flow, no work can be done. The universe will be dead in a thermodynamic sense. But that's trillions upon trillions of years in the future. For now, the universe is still young and dynamic. Stars are still forming and dying. Galaxies are still evolving, and in special places like the Boomerang Nebula, nature creates extremes that teach us about the fundamental laws governing reality. Let's return to Earth for a moment and think about how humans have learned to create cold. The ability to produce low temperatures has been one of the great technological achievements of the past few centuries. In the 1700s, scientists began systematically studying gases and how they behave when compressed or expanded. They discovered that gases heat up when compressed and cool when expanded. This led to the development of refrigeration technology in the 1800s. Early refrigerators used ammonia or sulfur dioxide as the refrigerant. These gases would be compressed by a pump, causing them to heat up. The hot gas would be cooled by passing it through coils exposed to air or water. Then the cooled gas would be allowed to expand, causing it to become very cold. This cold gas would absorb heat from the interior of the refrigerator, keeping food cold. Refrigeration revolutionized food storage and distribution. It allowed fresh food to be transported long distances. It made air conditioning possible, changing where people could comfortably live. But from a physics standpoint, refrigeration is also a triumph of thermodynamics. It's a practical application of the laws governing heat and energy, and it paved the way for reaching even lower temperatures. In the late 1800s, scientists began to liquefy gases. Here, oxygen was liquefied in 1877 at 90 Kelvin. Nitrogen was liquefied at 77 Kelvin. These achievements required understanding the behavior of gases under high pressure and low temperature. They required sophisticated equipment and careful control, but they opened new frontiers in physics and chemistry. Liquid air became a tool for laboratory experiments. Scientists could study how materials behaved at very low temperatures. Helium was the last gas to be liquefied. It was finally achieved in 1908 by Heike Kamerlingh-Onnes at Leiden University in the Netherlands. Helium liquefies at about 4 Kelvin, the coldest of any element, because helium atoms are so light and interact so weakly. Liquefying helium was a monumental achievement. It gave scientists access to temperatures within a few degrees of absolute zero for the first time. Kamerlingh-Onnes used this capability to discover superconductivity in mercury at temperatures below 4 Kelvin. This discovery revolutionized physics and led eventually to practical applications like MRI machines and powerful electromagnets. But scientists didn't stop at 4 Kelvin. They developed techniques to go even colder. One method is to reduce the pressure above liquid helium, causing some of it to evaporate. Evaporation is a cooling process. The molecules with the highest energy escape as gas, leaving behind cooler molecules in the liquid. By continuously pumping away the helium vapor, you can cool the remaining liquid to below 1 Kelvin. This is how temperatures around 0.3 Kelvin were first achieved. To go even colder requires more sophisticated techniques. One approach is dilution refrigeration, which uses a mixture of 2 isotopes of helium, helium-3 and helium-4. These isotopes behave differently at low temperatures due to quantum effects. By carefully manipulating the mixture, scientists can achieve temperatures of about 10 millikelvin or 0.01 Kelvin. This is 100 times colder than the Boomerang Nebula. Dilution refrigerators are used in research laboratories to study quantum mechanics at its most fundamental level. But the coldest temperatures ever achieved didn't use refrigerators in the traditional sense. They used lasers. In the 1990s, physicists developed laser cooling techniques that could slow down individual atoms by bombarding them with carefully tuned laser light. When an atom absorbs a photon, it gains momentum. But if the photon is coming from the opposite direction to the atom's motion, the atom slows down. By surrounding atoms with lasers from all directions, scientists can slow them to nearly a standstill. This cools them to temperatures of microkelvin, millionths of a degree above absolute zero. Taking this even further, evaporative cooling can be applied to laser-cooled atoms. Just like with liquid helium, allowing the fastest atoms to escape leaves behind slower, colder atoms. Using these techniques, scientists have reached temperatures of a few nanokelvin, billionths of a degree above absolute zero. At these temperatures, atoms behave in truly bizarre ways. They form Bose-Einstein condensates, where thousands of atoms synchronize their quantum states and behave as a single quantum object. This is matter at its most quantum, where the wave nature of particles completely dominates. These ultra-low temperature experiments have led to breakthroughs in quantum physics. They've allowed scientists to test fundamental theories with unprecedented precision. They've revealed new states of matter, and they're paving the way for technologies like quantum computers, which might someday revolutionize computing by harnessing quantum mechanics. So, humans have beaten nature at the cold game. We can create temperatures millions of times colder than the Boomerang Nebula. We've reached billionths of a degree above absolute zero, closer to the ultimate limit than any natural process. But there's a difference. The Boomerang Nebula achieves its cold temperature across a volume of space larger than our entire solar system. It contains the mass of 1/10 of a sun. The human-made ultra-cold experiments involve tiny clouds of a few thousand atoms in a space smaller than a pinhead. The scales are incomparable. Nature creates cold across cosmic scales. Humans create even colder temperatures, but only in vanishingly small amounts and for brief moments. Both tell us something important. Nature shows us that the laws of physics apply everywhere, from Earth laboratories to dying stars thousands of light years away. The same thermodynamic principles that govern refrigerators also govern stellar nebulae. And human achievement shows that we can push the boundaries, reaching temperatures and conditions that don't naturally exist, exploring physics in regimes nature doesn't access. Together, natural and artificial cold teach us about the fundamental nature of temperature, energy, and the quantum world. There's something profound about pushing toward absolute zero that goes beyond just achieving low temperatures. It's about exploring the limits of reality itself. Absolute zero represents a boundary, a place where classical physics breaks down completely and quantum mechanics takes over. It's a frontier as fundamental as the speed of light or the Planck length. And studying what happens near this frontier reveals deep truths about the nature of matter and energy. One of the strangest things about extreme cold is that it reveals quantum mechanics in everyday-sized objects. Normally, quantum effects are invisible to us. They happen at atomic scales, involving individual particles. But at temperatures close to absolute zero, quantum effects can manifest in macroscopic objects. Superconductors are one example. Below a critical temperature, certain materials conduct electricity with exactly zero resistance. An electric current set up in a packet, superconducting loop will flow forever without diminishing. This happens because electrons form Cooper pairs, bound states held together by quantum interactions with the material's atomic lattice. These pairs move through the material in a coordinated quantum state that can't be scattered by impurities or thermal vibrations. Another example is superfluidity. Liquid helium below 2.17 Kelvin becomes a superfluid. It flows without viscosity. If you put superfluid helium in a container, it will creep up the walls and flow out. It can flow through cracks too small for normal liquids to pass through. It creates strange fountain effects where the liquid spontaneously flows toward warmer regions. Superfluidity is a quantum phenomenon where helium atoms overlap their quantum wave functions and move as a single coherent quantum entity. It's one of the most direct manifestations of quantum mechanics at a scale we can see with our eyes. Bose-Einstein condensates take this even further. At temperatures below a few microkelvin, certain atoms can all occupy the same quantum state. They become indistinguishable. Their individual identities merge into a collective quantum wave function. The condensate behaves like a single giant atom. You can observe quantum interference patterns with it. You can manipulate it using magnetic and optical fields. It's matter that behaves more like a wave than like particles. Bose-Einstein condensates were first created in 1995, and they've been a tool for studying quantum mechanics ever since. They've revealed effects like atom lasers, quantum vortices, and matter wave interference. They might someday be useful for building ultra-precise sensors or quantum computers. All of these phenomena, superconductivity, superfluidity, Bose-Einstein condensation, require temperatures close to absolute zero because they're quantum effects that are normally destroyed by thermal energy. Thermal energy causes random motion, disrupts the delicate quantum correlations that these phenomena depend on. Only at very low temperatures, where thermal energy is minimal, can quantum coherence survive long enough for us to observe and study these effects. This is why ultra-low temperature physics is so important. It's the gateway to understanding quantum mechanics at a practical, tangible level. Now, let's think more carefully about what absolute zero actually means. We've said it's the lowest possible temperature, the point where molecular motion reaches its quantum mechanical minimum. But why is there a minimum? Why can't things just stop moving entirely? The answer is Heisenberg's uncertainty principle, which is one of the fundamental laws of quantum mechanics. The uncertainty principle states that certain pairs of properties like position and momentum cannot both be known precisely at the same time. The more precisely you know one, the less precisely you can know the other. If particles were perfectly at rest, their momentum would be exactly zero. We'd know their momentum with perfect precision, but then, according to the uncertainty principle, their position would be completely uncertain. They could be anywhere. This is a problem because particles are confined to finite regions. An electron is confined to an atom. A nucleus is confined to the center of an atom. These confinements impose limits on how uncertain the position can be, and if position uncertainty is limited, momentum uncertainty must be non-zero. The particle must have some motion, some spread in momentum values. This residual motion at absolute zero is the zero-point motion, and the energy associated with it is zero-point energy. Zero-point energy is not just a theoretical curiosity, it has measurable effects. One example is the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, they experience an attractive force. This force arises from quantum fluctuations in the electromagnetic field, which are a consequence of zero-point energy. The vacuum isn't truly empty. It's filled with quantum fields that fluctuate, creating and annihilating virtual particles. Between the plates, some wavelengths of these fluctuations are suppressed because they don't fit in the narrow gap. Outside the plates, all wavelengths are present. This imbalance creates a pressure that pushes the plates together. The Casimir effect has been measured experimentally and confirms that zero-point energy is real. Another manifestation of zero-point energy is in the properties of helium. Helium is the only substance that remains liquid at absolute zero under normal pressure. All other substances freeze solid. Why doesn't helium freeze? Because its atoms are very light and they interact weakly. The zero-point motion of helium atoms is large enough to prevent them from settling into a fixed crystal lattice. They keep moving, keep flowing, even at absolute zero. Only if you apply pressure of about 25 atmospheres can you force helium to solidify. Under high pressure, the atoms are squeezed close enough that their interactions overcome the zero-point motion, and the liquid freezes into a solid. This tells us something deep. Absolute zero is not a state of perfect stillness. It's a state of minimum motion, but motion nonetheless. The universe is fundamentally restless, even in the coldest, most motionless conditions we can imagine. Quantum mechanics ensures that particles keep moving, fields keep fluctuating, energy keeps existing. Absolute stillness is impossible. Nature forbids it. There's also the question of whether absolute zero exists as a real physical state, or whether it's just a mathematical concept. Thermodynamics says you can approach it but never reach it. The third law states that reaching absolute zero would require infinite time or infinite resources. Each step of cooling gets progressively harder. It's like trying to count to infinity. You can count higher and higher, but you'll never finish. Similarly, you can cool lower and lower, but you'll never reach exactly 0 Kelvin. And quantum mechanics adds another layer. Even if you could somehow remove all thermal energy, 0-point energy would remain. So, absolute zero as a state of zero energy doesn't exist. It's a limit, an asymptote, a boundary you approach but never touch. Yet, despite being unreachable, absolute zero is incredibly useful as a reference point. It gives us a natural scale for measuring temperature. The Kelvin scale starts at absolute zero and goes up. 0 Kelvin is the same for everyone, everywhere in the universe. It's based on fundamental physics, not on arbitrary choices like the freezing point of water. This makes the Kelvin scale the preferred scientific temperature scale. When physicists and chemists talk about temperature, they almost always use Kelvin because it directly relates to the energy in the system. Understanding temperature in terms of energy also helps us understand why some processes only happen at certain temperatures. Chemical reactions, for instance, often require activation energy. Molecules need enough kinetic energy to overcome barriers and rearrange into new configurations. At low temperatures, few molecules have this energy. Reactions slow down or stop. This is why refrigeration preserves food. It slows the chemical reactions and biological processes that cause decay. At very low temperatures, even simple processes like diffusion become incredibly slow. Atoms and molecules barely move. This is useful for preserving delicate structures, which is why biological samples are often stored in liquid nitrogen. On the other hand, some processes are enhanced at low temperatures. Quantum tunneling, for example, can become the dominant mechanism for certain reactions at very low temperature bays. Tunneling allows particles to pass through energy barriers they couldn't classically overcome. At high temperatures, particles have enough energy to go over the barrier. At low temperatures, they don't, so tunneling becomes important. This has implications for chemistry in cold environments like interstellar clouds or icy moons. Reactions that wouldn't happen at room temperature can proceed through tunneling at low temperatures, creating molecules that wouldn't otherwise form. Another interesting aspect of cold is how it affects light and radiation. All objects emit thermal radiation. The hotter an object, the more radiation it emits, and the shorter the wavelength of that radiation. Hot objects glow visibly. The sun's surface at about 6,000 Kelvin emits lots of visible light. A light bulb filament at a few thousand Kelvin glows white or yellow. Room temperature objects emit infrared radiation, which we can't see but can feel as heat. Very cold objects emit very little radiation, and what they do emit is at very long wavelengths in the microwave or radio range. This is how we detect cold objects in space. We use infrared and radio telescopes. The Boomerang Nebula, for example, was discovered and studied using infrared and radio observations. Its thermal emission is too weak and too long wavelength to be visible to optical telescopes. But radio telescopes can detect the faint glow of its molecules, measure their emission lines, and determine the temperature. This technique of using thermal radiation to measure temperature is fundamental to astronomy. It's how we determine the temperatures of stars, planets, nebulae, and even the cosmic microwave background. Speaking of the cosmic microwave background, let's think about what it tells us about the universe's temperature history. The CMB has a nearly perfect blackbody spectrum with a temperature of 2.73 Kelvin. This spectrum is exactly what you'd expect from an object in thermal equilibrium radiating according to its temperature. The fact that the CMB has this spectrum tells us that the early universe was in thermal equilibrium, that it was hot and dense, and that particles and radiation were constantly interacting, exchanging energy until they reached a common temperature. As the universe expanded, it cooled, but it maintained this thermal equilibrium until it became transparent at about 380,000 years after the Big Bang. Since then, the photons of the CMB have been traveling freely through space. Their wavelengths have been stretched by the expansion of the universe, which is why they've cooled from about 3000 Kelvin to 2.73 Kelvin. This expansion redshift is a direct consequence of general relativity. Space itself is expanding, and as it does, the wavelengths of photons stretch. Longer wavelengths correspond to lower energies and lower temperatures. So, the cooling of the CMB is a direct measurement of how much the universe has expanded since the time of recombination. In the future, as the universe continues to expand, the CMB will continue to cool. Its temperature will drop toward 0 Kelvin, though it will never quite reach 0 as long as the expansion continues at a finite rate. Eventually, perhaps in the far, far future, the CMB temperature might drop below 1 Kelvin, making the average temperature of the universe colder than the Boomerang Nebula is today. But by that time, the Boomerang Nebula will long since have warmed up and dispersed. So it will still hold the title of the coldest place in the universe, at least for its brief moment in cosmic history. All of this connects back to entropy and the arrow of time. The second law of thermodynamics states that entropy tends to increase in isolated systems. This is why hot and cold objects reach thermal equilibrium when put in contact. Heat flows from hot to cold until temperatures equalize. This is also why the universe is cooling. The universe started in a very low entropy state, hot and dense but uniform. As it expands and cools, entropy increases. Structures form, galaxies and stars and planets. But overall, the universe is heading toward a state of maximum entropy, where everything's at the same temperature, where no useful energy differences exist. This is the heat-death scenario, the ultimate fate of the universe if current cosmological models are correct. But that's trillions of years away. For now, the universe is full of temperature differences, of energy flows, of stars burning and planets forming and dying stars creating cold nebulae. And in studying these temperature extremes, we learn about the forces and laws that shape reality. The Boomerang Nebula at 1 Kelvin is a natural laboratory showing us thermodynamics in action on a cosmic scale. It's a reminder that the same laws that govern ice cubes melting and steam engines running also govern the death of stars and the cooling of the cosmos. There's one more aspect of the Boomerang Nebula worth exploring. Its discovery and study exemplify how modern astronomy works. We can't visit the Boomerang Nebula. We can't send a spacecraft there. It's 5,000 light years away, which, with current technology, would take millions of years to reach. Everything we know about it comes from light, from electromagnetic radiation that has traveled across space for 5,000 years to reach our telescopes. This light carries information encoded in its intensity, wavelength, and polarization. By carefully analyzing this information, astronomers can deduce the nebula's temperature, composition, structure, and dynamics without ever physically touching it. The process begins with observation. Telescopes collect light from the nebula. Different telescopes observe different wavelengths. Optical telescopes see visible light. Infrared telescopes see thermal radiation from dust. Radio telescopes detect emission from molecules. Each wavelength regime provides different information. Optical light shows us the nebula's overall structure, the distribution of ionized gas glowing in response to the central star's ultraviolet radiation. Infrared shows us dust, which absorbs starlight and re-radiates it as heat. Radio observations reveal molecules like carbon monoxide, whose emission lines tell us about temperature, density, and velocity. Spectroscopy is particularly powerful. When we split light into its component wavelengths, creating a spectrum, we see bright emission lines and dark absorption lines. Each line corresponds to a specific transition between energy levels in an atom or molecule. The wavelength of the line tells us which element or molecule is present. The intensity tells us how much is there. The width of the line tells us about temperature and turbulence. And the shift of the line from its rest wavelength tells us about velocity through the Doppler effect. In the Boomerang Nebula, carbon monoxide emission lines were crucial for determining the temperature. Carbon monoxide molecules rotate, and the energy levels of these rotational states are quantized. By measuring the relative intensities of different rotational transitions, astronomers can determine the population distribution across energy levels. This distribution follows a pattern determined by temperature. At high temperatures, many levels are populated. At low temperatures, only the lowest levels have significant population. By fitting the observed pattern to theoretical models, astronomers determined that the gas must be at about 1 Kelvin. This measurement was done from Earth across 5,000 light-years of space using radio waves emitted by molecules and the laws of quantum mechanics to interpret those waves. This is the power of astrophysics. We can learn intimate details about objects we'll never touch, places we'll never visit, using only light and the laws of physics. It's a testament to human ingenuity and to the universality of physical law. The quantum mechanics that governs carbon monoxide molecules in a laboratory here on Earth is the same. Quantum mechanics that governs those molecules in the Boomerang Nebula. The thermodynamics that predicts adiabatic cooling in a spray works the same way in an expanding stellar nebula. Physics is truly universal. This universality gives us confidence that our understanding of the Boomerang Nebula is correct. We can't check our answer by going there with a thermometer, but we can use multiple independent methods, different molecules, different transitions, different wavelengths, and they all agree. The temperature is 1 Kelvin. The expansion velocity is 170 kilometers per second. The mass is about 0.1 solar masses. These numbers form a coherent picture that makes sense within our broader understanding of stellar evolution and thermodynamics. This internal consistency is a sign that we're on the right track, that we truly understand what's happening 5,000 light years away. The Boomerang Nebula also serves as a reminder of the life cycles of stars. Our Sun, a middle-aged star currently fusing hydrogen in its core, will eventually die in a similar way. In about 5 billion years, the Sun will exhaust its hydrogen fuel. Its core will contract and heat up. The outer layers will expand, and the Sun will become a red giant, swelling to perhaps the orbit of Earth or Mars. It will shed its outer envelope in pulses, creating a planetary nebula not unlike the Boomerang Nebula, though probably not as cold. The Sun's core will be exposed as a white dwarf, hot and small, and over trillions of years, that white dwarf will cool, fading slowly into darkness. All stars with masses between about half a solar mass and 8 solar masses follow this path. They fuse hydrogen, then helium if they're massive enough. Then they shed their outer layers and become white dwarfs. More massive stars, above 8 solar masses, have different fates. They fuse heavier and heavier elements in their cores, building up an iron core that eventually collapses, triggering a supernova explosion. The core becomes a neutron star or a black hole. Less massive stars, below about half a solar mass, burn their hydrogen so slowly that none have yet reached the end of their main sequence lifetime. The universe isn't old enough. These tiny red dwarfs will outlive everything else, burning for trillions of years before finally fading away. But for stars like the Sun, the planetary nebula phase is the final act. It's brief, lasting only tens of thousands of years. The nebula expands, disperses, and merges back into the interstellar medium. The white dwarf cools over billions of years, and the material that once was part of the star spreads through space, eventually mixing with other gas and dust, perhaps someday forming new stars and planets. We ourselves are made of such material. Every atom in your body, heavier than hydrogen, was forged in a star's core through nuclear fusion and scattered into space when that star died. We are, quite literally, stardust. The Boomerang Nebula is a reminder of this cycle, a snapshot of stellar death that connects to our own origins. Understanding this connection gives us perspective. We're part of the universe, not separate from it. The same elements, the same physics, The same processes that govern the Boomerang Nebula govern us. We're temporary arrangements of atoms that will one day disperse back into the cosmos. But for now, we're here, conscious and curious, able to study the universe and understand our place in it. And that's extraordinary. The universe has evolved structures capable of comprehending the universe itself. Stars create the elements, planets form, life arises, intelligence emerges, and intelligence looks out at the cosmos, sees a nebula 5,000 light-years away, measures its temperature, and understands why it's the coldest place in the known universe. There's a beauty in that, a profound sense of connection and meaning. The Boomerang Nebula won't hold its record forever. Someday, either nature will create an even colder place through some process we haven't yet discovered, or humans will create colder temperatures in laboratories and perhaps even in space. But for now, this dying star 5,000 light-years away, expanding its gas at incredible speeds and cooling it to 1 Kelvin, stands as the coldest known natural place in the cosmos. It's a monument to stellar death, to thermodynamics, to the inexorable march toward entropy and the heat death of the universe. And it's a reminder that the universe is full of extremes, of places that challenge our understanding and push the boundaries of what we thought possible. The coldest place in the known universe is colder than the space between galaxies, colder than the cosmic background radiation, colder than almost anywhere else. And yet it exists, created by natural processes, following the same laws of physics that govern everything from spray cans to stellar nebulae. Think about what it means to measure 1 Kelvin, 1 degree above absolute zero. At this temperature, if you could somehow be there and survive, you'd be in an environment where thermal energy has nearly vanished. Molecules would be moving at a crawl by cosmic standards. Chemical reactions would have stopped. The gas would be so cold that on Earth it would instantly condense into a solid, crystallizing out of the air. But in the near vacuum of the nebula, the molecules are too far apart to find each other and stick together. They drift through space, each one isolated, each one barely moving, together forming this vast cloud of the coldest material in nature. And this cold is temporary. The Boomerang Nebula is changing even as we observe it. The gas is still expanding, still moving outward at 170 kilometers per second. As it expands, it spreads out. The density decreases. The expansion rate gradually slows as the gas loses energy to radiation and to interactions with the surrounding interstellar medium. Eventually, perhaps in a few thousand years, the expansion will slow enough that the gas stops cooling. It will begin to warm up, absorbing energy from starlight and cosmic radiation. The temperature will rise, the nebula will blend into its surroundings, becoming just another patch of interstellar gas, unremarkable and not particularly cold. But for this moment in cosmic time, for these few thousand years out of the 13.8 billion year history of the universe, the Boomerang Nebula holds the record. It's the coldest place we know, and studying it teaches us about the extremes of nature, about the physics of cold, about stellar death, and about the thermodynamic fate awaiting all things in the universe. The Boomerang Nebula represents something profound about our universe. It shows us that even in death, stars can create wonders. Even as they fade, they can produce conditions more extreme than anything in the ordinary cosmos. This dying star, shedding its outer layers, has accidentally created the coldest known natural environment through nothing more than rapid expansion and thermodynamics. There's no intent, no design, just physics playing out according to immutable laws. And yet the result is extraordinary. 1 Kelvin, 1 degree above the ultimate limit. The coldest place in the known universe, waiting out there in space, teaching anyone who looks closely about the nature of temperature, energy, and cosmic endings. But humans have pushed even further than nature in the quest for cold. In laboratories around the world, scientists have created temperatures that make the Boomerang Nebula look almost warm by comparison. We've reached billionths of a degree above absolute zero, temperatures so low that quantum mechanics completely dominates and matter behaves in ways that seem impossible. These achievements didn't happen overnight. They required decades of innovation, new technologies, and deep understanding of physics, and they've opened doors to studying nature in regimes that don't exist anywhere naturally in the universe. The journey to ultra-low temperatures began in the early 20th century when scientists first liquefied helium. Heike Kamerlingh-Onnes achieved this in 1908 at Leiden University, reaching temperatures around 4 Kelvin. This was a monumental achievement. Helium had resisted all previous attempts at liquefaction because it's so light and its atoms interact so weakly. But Onnes succeeded by using a cascade method, first cooling with liquid nitrogen at 77 Kelvin, then with liquid hydrogen at 20 Kelvin, and finally compressing and expanding helium gas in stages until it liquefied. This gave scientists access to temperatures within a few degrees of absolute zero for the first time in history. With liquid helium, Onnes discovered superconductivity. He found that Mercury's electrical resistance dropped to exactly zero below about 4 Kelvin. Current could flow through a superconducting loop forever without any energy loss. This was completely unexpected. Classical physics predicted that resistance should decrease as temperature dropped, but nobody expected it to vanish entirely. Superconductivity turned out to be a quantum mechanical phenomenon, explainable only through the strange rules of quantum physics. It would take decades before physicists fully understood it, but Onnes had opened a new frontier in physics with his liquid helium. Scientists soon pushed below 4 Kelvin by reducing the pressure above liquid helium, causing some of it to evaporate. Evaporation is a cooling process because the molecules with the highest energy escape, leaving behind cooler molecules. By continuously pumping away the helium vapor, temperatures below 1 Kelvin were achieved. This is actually colder than the Boomerang Nebula. Scientists in the 1920s and 30s, working in laboratories with equipment that would seem primitive by today's standards, were creating colder conditions than exist anywhere naturally in the cosmos. They didn't know about the Boomerang Nebula yet. It wouldn't be discovered for another 50 years, but they were already beating nature at the cold game. The next major breakthrough came with dilution refrigeration in the 1960s. This technique uses a mixture of two isotopes of helium, helium-3 and helium-4. These isotopes have different quantum properties. Helium-4 is a boson, meaning many atoms can occupy the same quantum state. Helium-3 is a fermion, meaning no two atoms can occupy the same state. When you mix the two isotopes and cool them below about 0.8 Kelvin, they separate into two distinct liquid phases, like oil and water. One phase is rich in helium-3, the other mostly helium-4. By carefully controlling this mixture, you can achieve continuous cooling down to about 10 millikelvin or 0.01 Kelvin. This is 100 times colder than the Boomerang Nebula. Dilution refrigerators became essential tools in low-temperature physics laboratories. They enabled the study of phenomena that only exist at these extreme temperatures. Scientists discovered new states of matter, measured quantum effects with unprecedented precision, and tested fundamental theories. But even 10 millikelvin wasn't the limit. Researchers wanted to go colder still, to explore regimes where quantum mechanics completely dominates and classical physics becomes irrelevant. The breakthrough came in the 1980s and 90s with laser cooling. This technique uses light to slow down atoms, and slowing atoms means cooling them. The idea is surprisingly simple. Atoms absorb photons from laser beams. When an atom absorbs a photon, it gains momentum in the direction the photon was traveling. But if you arrange lasers to shine from all directions and tune them carefully, atoms moving in any direction will preferentially absorb photons that oppose their motion. The net effect is that atoms slow down, like experiencing friction. But it's not friction from colliding with other atoms. It's friction from light itself. The catch is that you need to tune the laser frequency very precisely. Atoms only absorb light at specific wavelengths corresponding to their energy level transitions. If the laser is at exactly the right frequency, atoms at rest would absorb it. But moving atoms experience a Doppler shift. An atom moving towards the laser sees the light blue shifted to higher frequency. An atom moving away sees it red shifted to lower frequency. By tuning the laser slightly below the absorption frequency, you create a situation where only atoms moving toward the laser are Doppler shifted into resonance and absorb photons. This selective absorption slows the atoms down in all directions. Laser cooling can bring atoms down to temperatures of a few microkelvin, millionths of a degree above absolute zero. At these temperatures, atoms are moving at speeds of just centimeters per second. You can see them with the naked eye as a glowing cloud suspended in a vacuum chamber, held in place by magnetic fields. This cloud of ultra-cold atoms is so cold that gravity becomes a significant factor. The atoms fall slowly under gravity, and scientists have to account for this in their experiments. It's strange to think about. These atoms are so cold, so slow, that Earth's gravity noticeably affects their motion over timescales of seconds. But scientists went even further. They developed evaporative cooling, which works like reducing pressure over liquid helium but applied to clouds of laser-cooled atoms. You trap atoms in a magnetic or optical trap. The trap is like a bowl, Atoms with higher energy can climb the sides of the bowl and escape. Atoms with lower energy stay at the bottom. By gradually lowering the height of the bowl's walls, you allow the hottest atoms to escape while keeping the coldest ones. The remaining atoms collide with each other, sharing energy and reaching a new thermal equilibrium at a lower temperature. Repeat this process, and you can cool the atoms down to nano-Kelvin, billionths of a degree above absolute zero. At these temperatures, something extraordinary happens. The atoms become so cold that their quantum wave functions overlap. Remember, quantum mechanics says particles are also waves. The wavelength associated with a particle is inversely proportional to its momentum. Slow particles have long wavelengths. At nano-Kelvin temperatures, atoms move so slowly that their wavelengths become comparable to the spacing between atoms. The wave functions spread out and overlap. The atoms lose their individual identities. They all settle into the same quantum state. They become a Bose-Einstein condensate, a new state of matter predicted by Einstein in 1925, but not created until 1995. Bose-Einstein condensates are bizarre. They behave like a single giant atom, thousands or millions of atoms synchronized into one quantum state. You can observe quantum interference with them, just like you can with individual photons in a double-slit experiment. You can create quantum vortices, whirlpools in the condensate where atoms rotate around a central axis. These vortices are quantized. The circulation can only take on specific values, multiples of a fundamental quantum of circulation. This is direct visual evidence of quantum mechanics operating at a macroscopic scale. The temperatures achieved in these experiments are astonishing. The coldest temperature ever recorded in a laboratory is about half a nano-Kelvin, achieved by a team at MIT in 2003. That's 0.00000005. Kelvin, it's 5/10 billionths of a degree above absolute zero. To put this in perspective, it's colder than the Boomerang Nebula by a factor of 2 billion. It's almost incomprehensibly close to absolute zero, and it's achieved not through massive stellar processes spanning light years of space, but in a tiny cloud of atoms smaller than a pinhead, suspended in a vacuum chamber in a laboratory. At these ultra-low temperatures, quantum mechanics reigns supreme. Atoms don't behave like little billiard balls anymore. They behave like waves that can interfere, diffract, and tunnel through barriers. The classical physics that works for everyday objects breaks down completely. You need quantum mechanics to describe what's happening, and this gives scientists a tool for studying quantum mechanics directly. Bose-Einstein condensates are quantum simulators. You can manipulate them, change their properties, and watch how they respond. You can create artificial quantum systems that mimic other systems you want to study. This has applications in understanding fundamental physics, developing quantum computing, and even studying exotic states of matter that might exist in neutron stars. There's also a connection to cosmology. In the very early universe, fractions of a second after the Big Bang, conditions were so extreme that quantum effects operated on cosmic scales. Phase transitions occurred that shaped the structure of space-time itself. By studying Bose-Einstein condensates and other ultra-cold quantum systems, physicists can create analogues of these cosmic phase transitions in the laboratory. They can watch how quantum fields behave during transitions from one state to another. This gives insights into events that happened 13.8 billion years ago. Events we can never directly observe, but can recreate in miniature in a lab. Another application of ultra-low temperatures is in quantum computing. Quantum computers exploit quantum superposition and entanglement to perform calculations that would be impossible for classical computers. But quantum states are fragile. They're destroyed by thermal noise. Even a tiny amount of heat can disrupt the delicate quantum coherence needed for computation. This is why many quantum computing approaches require cooling to millikelvin or microkelvin temperatures. Superconducting qubits, one of the leading technologies for quantum computers, operate at temperatures around 0.01 Kelvin, maintained by dilution refrigerators. At these temperatures, thermal fluctuations are suppressed enough that quantum states can persist long enough to perform calculations. The pursuit of cold has also led to practical technologies. Superconducting magnets cooled with liquid helium are used in MRI machines, which revolutionized medical imaging. Particle accelerators like the Large Hadron Collider use superconducting magnets cooled to below 2 Kelvin to generate the enormous magnetic fields needed to steer particles around the accelerator ring. Infrared detectors used in astronomy are often cooled to liquid nitrogen temperatures or below to reduce thermal noise and detect faint signals from distant galaxies. Quantum sensors cooled to ultra-low temperatures can measure magnetic fields, gravitational fields, and time with unprecedented precision. These sensors might someday detect gravitational waves, navigate spacecraft, or search for dark matter. There's something philosophically interesting about the relationship between natural cold and human-made cold. Nature created the Boomerang Nebula at 1 Kelvin through stellar processes operating over thousands of years across volumes of space larger than our solar system. Humans created half a nanokelvin in a laboratory using lasers, magnetic fields, and quantum mechanics applied to a cloud of atoms for a few seconds. The natural process is grand, cosmic, involving the death of a star. The human process is precise, controlled, involving careful manipulation of individual atoms. Both teach us about the fundamental limits of temperature and the behavior of matter. Both push toward absolute zero, that unreachable boundary. And yet, absolute zero remains unreachable. No matter how sophisticated our technology becomes, we can't get there. The third law of thermodynamics forbids it. Every cooling step gets progressively harder. To cool from 1 Kelvin to 0.1 Kelvin requires removing 90% of the thermal energy. To cool from 0.1 to 0.01 requires removing 90% again. Each factor of 10 reduction in temperature requires removing another 90% of what remains. You approach zero asymptotically, getting closer and closer, but never arriving. This isn't a technological limitation, it's a fundamental property of nature, and it's connected to quantum mechanics. At absolute zero, a system would be in its ground state, its lowest possible energy state. But quantum mechanics requires uncertainty. Position and momentum can't both be precisely known. Energy and time can't both be precisely known. There's always fluctuation, always uncertainty, always some residual energy. This is 0-point energy, and it means absolute zero is a concept, a limit, but not an achievable physical state. 0-point energy has real consequences. It prevents helium from freezing under normal pressure, even at absolute zero. It creates the Casimir effect, where metal plates in a vacuum experience an attractive force due to quantum fluctuations. It contributes to the cosmological constant, the mysterious dark energy causing the universe's expansion to accelerate. 0-point energy is everywhere, always present, even in the purest vacuum. The vacuum isn't empty, it's seething with quantum fluctuations, particle-antiparticle pairs popping into existence and annihilating, electromagnetic fields fluctuating. This quantum foam is part of the fabric of reality. Understanding extreme cold also helps us understand the fate of the universe. The second law of thermodynamics states that entropy increases in isolated systems. The universe as a whole is an isolated system, so its entropy is increasing. One consequence is that temperature differences are gradually disappearing. Hot things cool down, cold things warm up, energy spreads out evenly. Stars burn their fuel and die. Galaxies exhaust their gas and stop forming new stars. Black holes evaporate through Hawking radiation over immense timescales. Eventually, in the unimaginably distant future, the universe reaches a state called heat death. All temperature differences vanish. Everything is at the same uniform temperature, just barely above absolute zero. No work can be done. No energy flows. The universe is thermodynamically dead. This heat death scenario is trillions of years in the future. Current estimates suggest that the last stars will burn out in about 100 trillion years. Black holes will evaporate over timescales of 10 to the 100 years or longer. The universe will expand and cool. The cosmic microwave background temperature, currently 2.73 Kelvin, will drop toward zero. Eventually, perhaps after 10 to the 100 years or more, the universe will consist of a dilute gas of photons, neutrinos, and possibly dark matter particles, all at a temperature infinitesimally close to absolute zero. This is the ultimate cold, not the cold of a dying star like the Boomerang Nebula, not the cold of a laboratory experiment, but the cold of a dead universe, expanded to near infinite size, its energy spread so thin that nothing can happen anymore. It's a sobering thought. Everything we see, all the stars and galaxies, all the complexity and beauty of the cosmos, is temporary. The universe is running down like a clock. Entropy is increasing. Temperature is equilibrating. And, in the end, cold and darkness and stillness. But that end is so far in the future that it's almost meaningless to us. The universe is young. It's only 13.8 billion years old. The first stars formed only a few 100 million years after the Big Bang. Galaxies are still evolving. Planets are still forming. Life arose on Earth and possibly elsewhere. The universe is dynamic and changing and far from equilibrium. The heat death is the ultimate fate, but it's not the current state and won't be for an incomprehensibly long time. In the meantime, we live in a universe with temperature gradients. Stars are hot, space is cold. This disequilibrium allows things to happen. Energy flows, work is done. Stars fuse hydrogen into helium and release energy. Planets form and cool. Life evolves and builds complex structures. All of this is possible because the universe isn't at equilibrium yet. We're living in the brief window between the hot Big Bang and the cold heat death when interesting things can occur. The Boomerang Nebula is part of this story. It's a transient cold spot in a universe that's still relatively warm and dynamic. It exists for a few thousand years, cools to 1 Kelvin through rapid expansion and then warms back up and disperses. It's a footnote in cosmic history, but it's a remarkable footnote. It shows us the extremes that natural processes can achieve. It demonstrates thermodynamics in action on a grand scale, and it reminds us that the universe is full of surprises, full of places and phenomena that challenge our expectations and expand our understanding. There's also beauty in cold itself. We often think of cold as harsh, as unpleasant. We bundle up against it. We heat our homes to avoid it. But cold has its own aesthetic. Ice crystals forming intricate patterns, frost on windows creating delicate structures, snow covering landscapes in pristine white. These are all manifestations of cold, of water molecules slowing down and arranging themselves into ordered structures. And at the extreme cold of the Boomerang Nebula or a Bose-Einstein condensate, there's a different kind of beauty. It's the beauty of simplicity, of systems stripped down to their quantum essentials, of nature approaching a fundamental limit. Physicists often speak of elegance in theories and experiments. Elegance means simplicity combined with power, a minimal set of principles that explain a wide range of phenomena. The physics of cold is elegant in this sense. A few fundamental laws, thermodynamics and quantum mechanics, explain everything from why your breath condenses on a cold day to why the Boomerang Nebula is one. Kelvin to why Bose-Einstein condensates form at nano-Kelvin. The same principles apply across all these scales. This universality is part of what makes physics beautiful. It's not just a collection of isolated facts. It's a coherent framework for understanding nature. Studying extreme cold has also taught us humility. Before scientists liquefied helium, many thought there was a limit to how cold things could get. That absolute zero was just a mathematical concept with no physical meaning. Then we reached helium temperatures and found superconductivity, a phenomenon nobody predicted. When we cooled below 1 Kelvin, we found superfluidity, another surprise. When we reached microkelvin, we created Bose-Einstein condensates, fulfilling a 70-year-old prediction. At every step, nature has revealed new physics, and there's no reason to think we've seen everything. Future experiments at even lower temperatures or in different systems might uncover phenomena we haven't imagined yet. This is why fundamental research matters. When Kamerlingh Onnes liquefied helium in 1908, he wasn't thinking about MRI machines or particle accelerators. He was pursuing basic scientific curiosity. He wanted to see what happens at low temperatures, but his work laid the foundation for technologies that have transformed medicine and physics. The same is true for laser cooling and Bose-Einstein condensates. When they were first achieved, they were scientific curiosities. Now they're being developed into quantum computers and precision sensors. You can't predict what applications will emerge from basic research, but history shows that understanding nature at a fundamental level always pays dividends, often in unexpected ways. The coldest place in the known universe, whether it's the Boomerang Nebula at 1 Kelvin or a laboratory cloud at half a nano Kelvin, is more than just a temperature record. It's a window into the fundamental nature of reality. It's where quantum mechanics becomes visible. It's where thermodynamics approaches its limits. It's where we test our theories against nature and learn whether our understanding is correct. And it's where we glimpse the ultimate fate of the universe, that far future when everything cools to near absolute zero and the cosmos reaches thermodynamic equilibrium. There's a connection between the cosmic and the quantum here. The Boomerang Nebula, a stellar nebula thousands of light years across, achieves 1 Kelvin through classical thermodynamics, through gas expansion and work and energy conservation. A Bose-Einstein condensate, a cloud of atoms micrometers across, achieves nano-Kelvin through quantum mechanics, through laser cooling and evaporation and quantum state manipulation. One is vast and natural, the other is tiny and artificial, but both are teaching us about the same fundamental concepts: temperature, energy, entropy, the approach toward absolute zero, the limits of what's possible, and both remind us that we're part of something larger. The atoms in the Boomerang Nebula were forged in a star's core billions of years ago. They underwent fusion, building up heavier elements from hydrogen. When the star died, it expelled these atoms into space. They're now part of the nebula, cooling as it expands. Someday, they'll disperse into the interstellar medium, mix with other gas and dust, and perhaps become part of new stars or planets. The same cycle that created us. The atoms in your body came from stars that died before the sun formed. You're made of recycled stardust, just like the Boomerang Nebula is made of recycled stardust. There's a continuity, a connection across space and time. The atoms in a Bose-Einstein condensate also have a history. They might be rubidium atoms, created in a supernova explosion billions of years ago, or sodium atoms, formed in a massive star's final moments. These atoms existed long before Earth formed. They witnessed the birth of the solar system. They've been part of rocks, oceans, living organisms. Now they're in a laboratory, cooled to nano-Kelvin, synchronized into a quantum state, serving as a tool for exploring physics. After the experiment ends, they're released, warmed back up, and eventually recycled. The cycle continues. Everything is connected. The coldest natural place and the coldest artificial place both emerge from the same physical laws governing the same atoms that make up everything in the universe. And understanding these connections gives us perspective on our place in the cosmos. We're not separate, observers looking at nature from the outside. We're part of nature, made of the same stuff, governed by the same laws. Our ability to study the universe, to create ultra-low temperatures, to understand quantum mechanics and thermodynamics, is the universe studying itself. Matter has organized into structures complex enough to comprehend matter. That's extraordinary. The story of cold is ultimately a story about limits and possibilities. Absolute zero is a limit, unreachable but approachable. The third law of thermodynamics sets boundaries on what we can do, but within those boundaries, there's vast room for exploration. We've cooled matter to billionths of a degree above absolute zero. We've created new states of matter. We've built technologies that seemed impossible decades ago. And we're still learning, still discovering, still pushing the boundaries of what's possible. Let's explore more deeply what happens in these ultra-cold quantum systems and why they matter so much to physics. When atoms are cooled to microkelvin or nanokelvin temperatures, they enter a regime where quantum mechanics completely dominates their behavior. At room temperature, atoms move at hundreds of meters per second. Their kinetic energy is large enough that quantum effects are washed out by thermal noise. You can treat them as classical particles following Newton's laws. But at microkelvin, atoms move at millimeters per second. Their de Broglie wavelength, the wavelength associated with their quantum wave nature, becomes hundreds of nanometers or even micrometers. This is comparable to or larger than the spacing between atoms in the cloud. When wave functions overlap like this, quantum mechanics takes over. One of the most striking demonstrations of quantum mechanics at ultra-low temperatures is quantum interference. In the famous double-slit experiment, you shoot photons or electrons at a barrier with two slits. Each particle goes through both slits simultaneously as a wave, interferes with itself, and creates an interference pattern on a screen. This pattern only makes sense if particles are waves that can be in multiple places at once. At ultra-low temperatures, you can do the same experiment with atoms. You split a Bose-Einstein condensate in half, let the two halves evolve separately, then bring them back together. They interfere, creating a pattern of alternating high and low atom density. This is matter-wave interference, atoms behaving as waves. It's quantum mechanics made visible and tangible. Another phenomenon is quantum tunneling. Classical mechanics says that a particle needs enough energy to climb over an energy barrier. If it doesn't have that energy, it can't get through. Quantum mechanics says differently. A particle can tunnel through a barrier even if it doesn't have enough energy to go over it. The probability is usually tiny, but it's non-zero. At ultra-low temperatures, tunneling can become the dominant mechanism for certain processes. Atoms can tunnel through barriers created by laser beams or magnetic fields. They can tunnel from one side of a potential well to the other. This has applications in studying chemical reactions at low temperatures, understanding how atoms move in crystals, and developing quantum devices. Superfluidity is another quantum phenomenon enhanced at ultra-low temperatures. We mentioned helium becoming a superfluid below 2.17 Kelvin, but Bose-Einstein condensates also exhibit superfluidity. A superfluid flows without viscosity. It can't dissipate energy through friction. If you stir a superfluid and create vortices, those vortices persist indefinitely. They can't slow down or decay as they would in a normal fluid. The vortices are quantized. The circulation around each vortex is an integer multiple of h over m, where h is Planck's constant and m is the atom's mass. This quantization is direct evidence that superfluidity is a quantum phenomenon. The applications of ultra-cold atoms and Bose-Einstein condensates extend beyond fundamental physics. One promising area is quantum simulation. Many quantum systems are too complex to solve exactly using classical computers. The equations describing how electrons interact in a material, or how quarks interact in a nucleus, or how quantum fields behave in the early universe are often impossible to solve analytically. Even numerical solutions require approximations that might miss important physics. Quantum simulators offer an alternative. You create an artificial quantum system in the lab, one that's mathematically equivalent to the system you want to study. Then you observe how the artificial system behaves. This gives you insights into the real system. Bose-Einstein condensates are ideal quantum simulators because you can control their properties with exquisite precision. You can adjust the strength of interactions between atoms using magnetic fields and Feshbach resonances. You can create artificial periodic potentials using standing waves of laser light, simulating how electrons behave in crystals. You can study phase transitions, quantum magnetism, exotic states of matter, and even phenomena that don't occur in nature but are predicted by theory. This has led to discoveries about how materials behave at the quantum level, discoveries that might inform the development of new materials with useful properties. Quantum computing is another application. A quantum computer uses quantum bits or qubits, which can exist in superpositions of 0 and 1 rather than being definitively one or the other. This allows quantum computers to perform certain calculations exponentially faster than classical computers. But building a quantum computer is extremely challenging. Qubits need to maintain their quantum coherence long enough to perform calculations. Thermal noise destroys coherence. This is why many quantum computing approaches require ultra-low temperatures. Superconducting qubits, one of the leading technologies, operate at temperatures around 10 to 20 millikelvin, achieved using dilution refrigerators. Trapped ion qubits operate at slightly higher temperatures but still require cooling to minimize thermal noise. Neutral atom qubits use laser-cooled atoms as qubits, taking advantage of the ultra-low temperatures achieved through laser cooling. Each approach has advantages and challenges, but all rely on cold to suppress thermal fluctuations that would otherwise destroy the delicate quantum states needed for computation. If quantum computers reach maturity, They could revolutionize cryptography, drug discovery, materials science, artificial intelligence, and many other fields. And they'll have cold to thank for making quantum coherence possible. Precision measurement is yet another application. Atomic clocks, which are the most accurate timekeeping devices ever built, benefit from ultra-low temperatures. The best atomic clocks use clouds of laser-cooled atoms. The cold atoms move slowly, which reduces the Doppler shift and allows more precise measurements of their transition frequencies. These clocks are so accurate that they would lose less than 1 second over the age of the universe. They're used to test general relativity, search for variations in fundamental constants, and provide time standards for GPS and telecommunications. Future quantum sensors might use Bose-Einstein condensates to measure gravitational fields, magnetic fields, or accelerations with unprecedented precision. These sensors could detect gravitational waves from distant black hole mergers, map underground geological structures, navigate spacecraft without GPS, or search for dark matter. The pursuit of ultra-low temperatures has also revealed new physics that wasn't predicted. The fractional quantum Hall effect, discovered in two-dimensional electron systems at low temperatures and high magnetic fields, showed that electrons can organize into exotic states with fractional electric charges. This was completely unexpected and led to new understanding of quantum matter. Topological insulators, materials that are insulators in their bulk but conduct electricity on their surfaces, were discovered through low-temperature experiments and have potential applications in quantum computing. High-temperature superconductors, which superconduct at temperatures up to about 130 Kelvin instead of the few Kelvin typical of conventional superconductors, remain mysterious decades after their discovery. Understanding them might lead to room temperature superconductors, which would revolutionize power transmission and electronics. Each of these discoveries emerged from studying matter at low temperatures where quantum effects dominate. And there's no reason to think we've seen everything. As technology improves, and we reach even lower temperatures or explore different materials and conditions, new phenomena will likely emerge. This is why fundamental research continues. We're still learning about the quantum world, still discovering new states of matter, still finding surprises. Now, let's think about what all of this means for our understanding of temperature itself. We started by defining temperature as a measure of average kinetic energy. Hot objects have fast-moving molecules. Cold objects have slow-moving molecules. This definition works well for classical systems, but at ultra-low temperatures, it becomes more complicated. When atoms form a Bose-Einstein condensate, they all occupy the same quantum state. What does temperature mean for such a system? You can define it thermodynamically through entropy and energy, but the intuitive picture of temperature as molecular motion breaks down. Similarly, quantum systems can have negative temperatures. This sounds impossible. How can something be colder than absolute zero? But negative temperature doesn't mean colder than 0 Kelvin. It means the system is in a population-inverted state, where higher energy levels are more populated than lower ones. This is unstable in most systems, but it can exist briefly in certain conditions. Negative temperature systems are actually hotter than positive temperature systems in the sense that heat flows from negative temperature to positive temperature systems. It's a strange consequence of how temperature is defined thermodynamically. Negative temperatures have been achieved in nuclear spins, in certain optical lattices with ultra-cold atoms, and in other exotic systems. These complications show that temperature is subtle. At everyday scales, it's simple. Things are hot or cold based on how fast their molecules move, but at quantum scales or in exotic systems, temperature becomes a more abstract concept tied to statistical mechanics and thermodynamics. It's still well defined, but it requires careful thought to understand what it means. This is typical of physics. Simple concepts at one scale become complicated at other scales. But the complications are part of the richness of nature. Let's also consider the practical challenges of achieving and maintaining ultra-low temperatures. It's not easy. A dilution refrigerator maintaining 10 millikelvin requires sophisticated engineering, careful temperature control, and isolation from external heat sources. The slightest vibration, stray light, magnetic field fluctuation, or thermal contact with the environment can heat the system. Labs that work at these temperatures use multiple layers of shielding, electromagnetic and thermal, to isolate their experiments. They use superconducting wiring to minimize heat conduction. They pump constantly to maintain vacuum. It's a constant battle against the second law of thermodynamics, which says heat flows from hot to cold. The lab is at room temperature, roughly 300 Kelvin. The experiment is at millikelvin or microkelvin. Heat wants to flow in. Preventing it requires constant effort and energy. For laser cooling and Bose-Einstein condensates, the challenges are different. You need ultra-high vacuum so atoms don't collide with background gas. You need powerful, stable lasers tuned to precise frequencies. You need magnetic fields to trap the atoms and compensate for stray fields. You need careful timing and control, often down to microseconds. Creating a Bose-Einstein condensate takes seconds to minutes of careful manipulation. Once created, it lasts seconds or less before heating up or dispersing. Each experimental run requires recooling a fresh batch of atoms. It's painstaking work, but it's necessary to access this quantum regime. The fact that we can achieve these temperatures at all is remarkable. Room temperature is about 300 Kelvin. Liquid nitrogen is 77 Kelvin. Liquid helium is 4 Kelvin. Dilution refrigerators reach 10 millikelvin. Laser cooling reaches microkelvin. Evaporative cooling reaches nanokelvin. That's a temperature span. From 300 Kelvin to nanokelvin, a factor of 300 billion. We've cooled things by a factor of 300 billion. That's comparable to shrinking something the size of Earth down to the size of a grain of sand. It's an astonishing range, and we've learned something at every temperature along the way. 77 Kelvin showed us how nitrogen liquefies and how materials behave when most thermal energy is removed. 4 Kelvin revealed superconductivity and superfluidity. 10 millikelvin enabled studies of quantum Hall effects and topological matter. Microkelvin gave us Bose-Einstein condensates. Nanokelvin is now pushing the boundaries of quantum simulation and precision measurement. Each decade of temperature reduction has opened new physics, new technologies, new understanding. This progression also mirrors the history of thermodynamics and quantum mechanics. In the 1800s, scientists developed thermodynamics to understand heat engines and efficiency. They discovered that temperature is related to energy and entropy. In the early 1900s, quantum mechanics revealed that energy is quantized, that particles are also waves, that there's fundamental uncertainty. Low-temperature physics brought these two frameworks together. Thermodynamics describes how systems approach equilibrium and how entropy increases. Quantum mechanics describes what happens at the microscopic level. At ultra-low temperatures, you need both to understand what's going on. They're complementary perspectives on the same reality. There's also a philosophical dimension to studying extreme cold. Absolute zero represents a kind of perfection, a state of minimum energy and maximum order. In some ways, it's the opposite of the chaos and randomness that characterize everyday life. At absolute zero, if we could reach it, a perfect crystal would have every atom in exactly the right place. There would be no thermal vibrations, no disorder, just crystalline perfection. Of course, quantum mechanics prevents this perfect stillness through zero-point motion, but the idea remains compelling. Absolute zero is a Platonic ideal, a limit we can imagine and approach but never quite achieve. This connects to deeper questions about the nature of reality. Why do physical laws have the form they do? Why is there a minimum temperature but no maximum temperature? You can heat things to arbitrarily high temperatures given enough energy. The core of a massive star can reach billions of degrees. Particle collisions at the Large Hadron Collider create temperatures trillions of degrees, reproducing conditions from microseconds after the Big Bang. There's no upper limit to temperature in principle, only practical limits based on how much energy you can concentrate. But there's a hard, lower limit at absolute zero. This asymmetry is built into the structure of thermodynamics and quantum mechanics. It tells us something fundamental about how the universe works. The second law of thermodynamics states that entropy increases. This gives time an arrow, a direction. The future is the direction of increasing entropy. The past is the direction of decreasing entropy. But why? Why does entropy increase? The answer lies in statistics. There are many more disordered states than ordered states. If you have a system and you allow it to evolve randomly, it will almost certainly move toward disorder simply because there are more ways to be disordered than ordered. A messy room is more likely than a tidy room if you're arranging things randomly. Heat spreading out is more likely than heat spontaneously concentrating. This statistical tendency toward disorder is what drives the second law. But this raises a puzzle. The early universe, just after the Big Bang, was in a very low entropy state. It was hot and dense, yes, but it was also extremely uniform. The cosmic microwave background shows this uniformity. Temperature variations were only about 1 part in 100,000. That's remarkable smoothness. If the universe started in maximum entropy, it would have been a chaotic mess, not a smooth expanding fireball. So why did it start with low entropy? This is called the past hypothesis, or the problem of initial conditions. We don't have a complete answer. It's one of the deep mysteries of cosmology. Whatever the reason, the universe started with low entropy and has been increasing entropy ever since. Stars form, burn, and die, converting ordered nuclear fuel into disordered thermal radiation. Galaxies cluster and merge, creating structure but increasing overall entropy. Black holes form and eventually evaporate, releasing entropy in the form of Hawking radiation. The expansion of the universe dilutes energy, cooling it down, increasing entropy. All roads lead to higher entropy, to more disorder, to the heat death where everything is at the same cold temperature and nothing interesting happens anymore. The Boomerang Nebula is part of this entropic journey. The star at its center created low entropy by fusing hydrogen into helium, converting diffuse energy into concentrated nuclear energy. But this process couldn't continue forever. Fusion produces entropy overall, and eventually the fuel runs out. The star dies, expelling its outer layers. The gas expands and cools, increasing entropy. The material disperses into space, mixing with other gas, approaching equilibrium. Entropy goes up. The universe marches toward heat death. The Boomerang Nebula's extreme cold is a local temporary phenomenon. It doesn't reverse the overall trend. It's a brief eddy in the river of increasing entropy. Understanding this gives us a sense of cosmic time. The universe is currently about 13.8 billion years old. Stars are still forming, galaxies are still evolving. We're in a relatively early phase cosmically speaking, but the long-term future is cooling and darkness. In 100 trillion years, the last, stars will have burned out, galaxies will be dead, filled with white dwarfs, neutron stars, and black holes. In 10 to the 100 years, black holes will have evaporated through Hawking radiation. The universe will be a cold, dark, expanding void with a temperature approaching absolute zero. This is the far future, the ultimate cold. But that's an unimaginably long time from now. For perspective, 100 trillion years is about 7,000 times the current age of the universe. 10 to the 100 years is so long that trying to comprehend it is futile. These are timescales on which even black holes seem ephemeral. Compared to these eons, human civilization is a flicker. Earth has existed for 4.5 billion years. Life has existed for perhaps 4 billion years. Humans have existed for a few 100,000 years. Civilization for a few thousand years. We're in the very beginning of cosmic history. The universe is young. It's still hot and bright and full of activity, and that's good for us. We need temperature differences to exist. Life requires energy flow. You can't run a heat engine without a temperature gradient. You can't do work without energy flowing from hot to cold. Life on Earth is powered by the sun, a hot object at 6,000 Kelvin, radiating energy into the cold of space at 3 Kelvin. This temperature difference drives everything. Sunlight heats the atmosphere and oceans, creating weather. Plants capture sunlight and convert it to chemical energy through photosynthesis. Animals eat plants or other animals, extracting that energy. The whole biosphere is a thermodynamic engine running on the temperature difference between the sun and space. In the far future, when the universe has cooled to near absolute zero and all temperature differences have vanished, life won't be possible. There will be no energy flow, no work, no complexity. The universe will be dead thermodynamically. But we're not there yet. We're in the age of stars and galaxies and planets and life. We're in the age when temperature differences exist and interesting things happen. And studying the extremes, both the hottest and coldest places, helps us understand this age and appreciate how special it is. The coldest place in the known universe, whether natural or artificial, also teaches us humility. We think we understand temperature. We've developed thermodynamics into a precise mathematical framework. We've built technologies that control temperature with incredible precision. We've cooled things to billionths of a degree above absolute zero. But there are still mysteries. We don't fully understand high-temperature superconductors. We don't know whether there's a maximum possible temperature. We don't know why the universe started with low entropy. We don't know if the heat death is truly inevitable or if new physics might intervene. These are open questions, reminders that our knowledge, while extensive, is incomplete. This is true across all of physics. We've mapped the electromagnetic spectrum from radio waves to gamma rays. We've understood atomic structure and nuclear physics. We've developed quantum mechanics and general relativity. We've discovered the Higgs boson and detected gravitational waves. We've observed the cosmic microwave background and measured the expansion rate of the universe. We've achieved an extraordinary understanding of nature. But we don't have all the answers. Dark matter and dark energy make up 95% of the universe, and we don't know what they are. We can't unify quantum mechanics and general relativity into a theory of quantum gravity. We don't know how life began or whether it exists elsewhere in the universe. Science is a work in progress, a continuous process of discovery and refinement. Studying extreme cold contributes to this progress. Every time we cool something to a new record temperature, we access a new regime where new physics might emerge. Every time we create a new quantum state or discover a new phenomenon, we expand our understanding. And this understanding has practical value. Superconductors enable powerful magnets for MRI machines and particle accelerators. Atomic clocks provide GPS timing and test fundamental physics. Quantum computers might someday revolutionize computing. All of these technologies emerged from basic research into the behavior of matter at low temperatures. Future technologies will emerge from current research. We can't predict exactly what they'll be, but history suggests they'll be transformative. There's also aesthetic value in understanding, knowing that the Boomerang Nebula is one. Kelvin doesn't make you warmer or richer, but it gives you a deeper appreciation for the universe. It connects you to something larger than everyday concerns. It shows you that nature is far stranger and more wonderful than common experience suggests. There's a dying star thousands of light years away, invisible to the naked eye, cooling itself through expansion to temperatures lower than the space around it. That's extraordinary, and knowing about it, understanding why it happens, seeing how it fits into the larger story of stellar evolution and thermodynamics, is enriching in a way that's difficult to quantify, but deeply valuable. The same is true for Bose-Einstein condensates and ultra-cold atoms. Knowing that scientists can cool atoms to nanokelvin and watch them behave quantum mechanically doesn't directly improve your life, but it shows you what humans are capable of. It demonstrates that we can push the boundaries of what's possible, that we can explore regimes of nature that don't exist anywhere naturally, that we can test our theories in the most extreme conditions and find that they work. This is inspiring. It's a testament to human ingenuity and curiosity and the power of science. And it's not finished. Scientists are currently working on next-generation experiments that will push even closer to absolute zero. They're developing techniques to cool molecules, not just atoms, to ultra-low temperatures. Molecules are more complex than atoms, with rotational and vibrational energy levels, in addition to translational motion. Cooling them is harder, but it opens new possibilities for chemistry at ultra-low temperatures and for quantum simulation of molecular systems. They're also exploring cooling in space, where microgravity allows longer interrogation times and weaker trapping potentials. The Cold Atom Lab on the International Space Station is already performing experiments with Bose-Einstein condensates in microgravity, achieving conditions impossible on Earth. Future space missions might create ultra-cold atom clouds in orbit around Earth or even in deep space, far from gravitational and magnetic perturbations. These could be used as quantum sensors to detect gravitational waves with unprecedented sensitivity, to test general relativity with extreme precision, or to search for dark matter. If dark matter consists of ultralight particles, it might interact with ultra-cold atoms in detectable ways. These experiments are pushing the boundaries of what's possible and what we can learn about the universe. Back on Earth, researchers are exploring topological quantum matter, exotic states where the arrangement of quantum states in abstract mathematical spaces gives rise to new physics. They're studying quantum critical points, transitions between quantum states that occur at absolute zero and are driven by quantum fluctuations rather than thermal fluctuations. They're investigating quantum chromodynamics at low temperatures, exploring how quarks and gluons behave in ultra-cold conditions. Each of these areas is active and growing, promising new discoveries in the coming years. The interplay between theory and experiment is crucial. Theorists predict new phenomena based on mathematical models and physical principles. Experimentalists devise ways to test these predictions. Sometimes experiments confirm theories. Sometimes they reveal surprises that send theorists back to the drawing board. This back and forth drives progress. Low-temperature physics has been particularly fruitful in this regard. Superconductivity was discovered experimentally and explained theoretically decades later. Bose-Einstein condensation was predicted theoretically and confirmed experimentally 70 years later. The quantum Hall effect was discovered experimentally and explained theoretically, leading to new mathematics and new physics. This synergy between theory and experiment makes physics a vibrant, dynamic field. It's worth noting that all of this, the study of extreme cold, the pursuit of absolute zero, the creation of quantum states, is a purely intellectual endeavor. We're not cooling things to survive. We're not doing it for immediate practical benefit. We're doing it because we're curious. We want to know how nature works. We want to test our theories. We want to explore the boundaries of the possible. This is what makes us human. We're not content with just surviving. We want to understand, and that understanding enriches us, gives our lives meaning, connects us to the larger cosmos. The Boomerang Nebula, that dying star 5,000 light-years away, doesn't know we're studying it. It doesn't care. It's just following the laws of physics, expanding and cooling and slowly dispersing. But we care. We built telescopes and spectrometers and theoretical models to study it. We calculated its temperature, understood its structure, explained why it's the coldest natural place in the universe. And in doing so, we learned about thermodynamics, about stellar death, about the connection between expansion and cooling. We connected this distant nebula to our own understanding of temperature and entropy and the fate of the universe. That connection is meaningful. It's what science is all about. Similarly, the scientists creating nano-Kelvin temperatures in laboratories around the world are driven by curiosity. They want to see what happens at these extreme temperatures. They want to test quantum mechanics in new regimes. They want to discover new phenomena and develop new technologies. It's challenging work requiring years of training, sophisticated equipment, and meticulous attention to detail. But it's rewarding. Every successful experiment, every new discovery, every confirmation of a theoretical prediction or surprise deviation adds to our collective understanding, and that understanding is shared. Papers are published, results are discussed at conferences, students learn the techniques and carry them forward, knowledge accumulates, builds on itself, grows. This is the scientific enterprise, a collaborative human effort to comprehend the universe. As we wrap up this exploration of the coldest place in the known universe, it's worth reflecting on the journey we've taken. We started with a simple question about temperature and cold. We learned that cold is the absence of heat, that temperature measures molecular kinetic energy, and that there's a fundamental lower limit at absolute zero. We discovered the Boomerang Nebula, a dying star 5,000 light-years away that's cooled itself to 1 Kelvin through rapid expansion, making it the coldest natural place we've ever found. We explored how scientists measure such extreme temperatures using spectroscopy and radio astronomy, analyzing light that's traveled across thousands of light-years to reach us. We then dove into the physics of approaching absolute zero, learning about the third law of thermodynamics, zero-point energy, and the quantum mechanical reasons why absolute zero can never quite be reached. We compared natural cold in places like Antarctica, interstellar space, and the Boomerang Nebula to the artificial cold achieved in laboratories through techniques like dilution refrigeration, laser cooling, and evaporative cooling. We saw how humans have created temperatures of nano-Kelvin, billionths of a degree above absolute zero, colder than anywhere in nature by factors of billions. We explored the strange quantum phenomena that emerge at these ultra-low temperatures. Superconductivity, where electrical resistance vanishes completely. Superfluidity, where liquids flow without viscosity. Bose-Einstein condensates, where thousands of atoms synchronize into a single quantum state, behaving like a giant matter wave. These phenomena are direct manifestations of quantum mechanics operating at scales we can see and manipulate, and they're teaching us about the fundamental nature of matter and energy. We discussed applications of ultra-cold physics, from quantum computers and precision atomic clocks to quantum sensors and quantum simulators. We saw how basic research into extreme cold has led to technologies like MRI machines, superconducting magnets, and infrared detectors that have transformed medicine, physics, and astronomy. And we glimpsed future possibilities, from space-based ultra-cold atom experiments to searches for dark matter to tests of general relativity with unprecedented precision. Throughout this journey, we've encountered deep themes: the relationship between temperature and entropy, the arrow of time pointing toward increasing disorder, the ultimate fate of the universe in the heat-death scenario where everything cools to near absolute zero and thermodynamic equilibrium is reached. The beauty and elegance of physical laws that apply equally to dying stars and laboratory experiments, to cosmic scales and quantum scales. The power of science to push boundaries, test theories, and discover new phenomena. We've also touched on philosophy. What does it mean that absolute zero is unreachable? What does it tell us about the structure of reality that there's a minimum temperature but no maximum? Why did the universe start in a low entropy state, and what does that say about the nature of time? These questions go beyond physics into deeper territory, connecting science with fundamental questions about existence and causality. We don't have complete answers, but asking the questions and exploring as far as we can is part of the scientific endeavor. The coldest place in the known universe represents an extreme, a boundary case that tests our understanding and reveals new physics. Whether it's the Boomerang Nebula at 1 Kelvin or a laboratory condensate at nano-Kelvin, extreme cold shows us nature at its most quantum, its most ordered, its closest approach to the theoretical limit of absolute zero. And studying these extremes teaches us about everything in between, including the moderate temperatures where life exists and flourishes. There's a poignancy to the Boomerang Nebula specifically. It's the final act of a star's life, a brief, spectacular phase before the material disperses and the white dwarf core fades away. The star created this cold through the violence of its death throes, expelling gas at incredible speeds, cooling it through expansion to temperatures lower than the cosmos itself. It's transient. In a few thousand years, it will warm and disperse. But for now, for this cosmic moment, it holds the record, the coldest natural place, a dying star's monument to thermodynamics. And there's inspiration in what humans have achieved. We've built machines that can cool atoms to nano-Kelvin. We've created Bose-Einstein condensates and watched quantum mechanics play out before our eyes. We've tested theories developed a century ago and found them correct to extraordinary precision. We've pushed the boundaries of what's possible and discovered new states of matter along the way. This demonstrates what we're capable of when we apply intelligence, creativity, and persistence to understanding nature. It's a triumph of the scientific method, of careful observation and mathematical modeling and experimental verification. The connection between the cosmic and the laboratory is profound. The same physical laws that govern the Boomerang Nebula also govern Bose-Einstein condensates. Thermodynamics applies equally to dying stars and refrigerators. Quantum mechanics describes both atoms in a laser-cooled cloud and the zero-point energy that keeps helium liquid at absolute zero. There's a unity to physics, a coherence that means understanding one system helps us understand others. This universality is part of what makes physics beautiful and powerful. Looking ahead, the study of extreme cold will continue. New experiments will push temperatures even lower or explore cold in new contexts. New technologies will emerge from basic research, technologies we can't predict, but that will likely transform society as previous discoveries have done. New phenomena will be discovered, challenging our theories and expanding our knowledge, and new questions will arise, because every answer in science leads to more questions. That's not a failure, it's a feature. It means there's always more to learn, always new frontiers to explore. For you, the listener, I hope this journey has given you a new appreciation for temperature and cold. Next time you feel cold on a winter day, remember that you're still far from absolute zero. You're at maybe 280 Kelvin, only 20 degrees colder than room temperature, vastly warmer than the Boomerang Nebula or a Bose-Einstein condensate. Next time you use a refrigerator or freezer, think about the thermodynamics at work. The compression and expansion of refrigerant gas, the flow of heat from cold to hot driven by energy input. Next time you hear about quantum computers or MRI machines, remember that they're built on discoveries made by scientists exploring extreme cold, pursuing knowledge for its own sake, and remember that the universe is vast and strange and full of extremes. The hottest places, the cores of massive stars, and the moments after the Big Bang reach billions or trillions of degrees. The coldest places, the Boomerang Nebula and ultra-cold atom clouds, approach absolute zero, just fractions of a degree above the ultimate limit. And in between, there's everything else. Stars and planets and galaxies, oceans and atmospheres and ice caps. Life in all its diversity, thriving in the narrow temperature range where liquid water exists and chemistry can build complex structures. We're part of this vast temperature landscape, occupying a tiny warm niche in a cosmos that spans from near absolute zero cold to arbitrarily hot. The coldest place in the known universe is a reminder of this cosmic diversity. It's a place where thermodynamics pushes toward its limits, where expansion creates cold that surpasses even the frigid void of intergalactic space, where a dying star's last act creates conditions more extreme than the background temperature of the universe itself. It's out there right now, 5,000 light years away, cooling and expanding according to the same physical laws that govern everything from atoms to galaxies. And understanding it, connecting it to laboratory experiments and theoretical frameworks, appreciating its place in the larger story of stellar evolution and cosmic cooling, is what science is all about. It's the human mind reaching out to comprehend the universe, finding patterns and principles, building knowledge that enriches us all. Every discovery about extreme cold adds another piece to our understanding of nature. When we learned that the Boomerang Nebula exists at 1 Kelvin, we confirmed that natural processes can create temperatures below the cosmic microwave background. This was surprising. It showed that local thermodynamic processes can override the background temperature of the universe, at least temporarily. When we created Bose-Einstein condensates at nano-Kelvin, we opened a window into pure quantum behavior, watching matter transform from classical particles to quantum waves. Each achievement builds on previous ones, creating a cumulative body of knowledge that grows over time. The story of cold spans from cosmic nebulae to quantum laboratories, from stellar death to atomic physics, unified by the same fundamental laws of thermodynamics and quantum mechanics. This knowledge has practical value beyond immediate applications. It trains minds to think rigorously about difficult problems. It develops technologies that find unexpected uses. The dilution refrigerator, developed to study fundamental physics, now enables quantum computers. The laser cooling techniques that created Bose-Einstein condensates now power atomic clocks used in GPS satellites. We can't predict what future applications will emerge from current research, but history suggests they'll be transformative. Understanding extreme cold today might enable technologies tomorrow that we haven't imagined yet. There's also intrinsic value in knowledge itself, knowing how the universe works, understanding why the Boomerang Nebula is cold, and what happens at nano-Kelvin enriches human culture, even if it never leads to practical applications. It's part of our collective heritage, like art or music or literature. The equation describing Bose-Einstein condensation is as beautiful as a symphony. The image of atoms synchronized in a quantum state is as moving as a painting. Science is a human creation, an attempt to make sense of the cosmos, and its achievements deserve to be celebrated alongside other human achievements. We pursue knowledge because we're curious, because we wonder, because understanding brings its own reward beyond utility. So, the next time you look up at the night sky, think about what's out there beyond the visible stars. Think about dying stars shedding their outer layers, creating nebulae that glow and cool and disperse. Think about the Boomerang Nebula, invisible to your eyes, but real and remarkable. The coldest place in nature, a testament to the power of thermodynamics and the inevitability of stellar death. And think about the scientists in laboratories around the world, cooling atoms to nano-Kelvin, creating quantum states, pushing the boundaries of the possible. Both are exploring cold, one naturally across cosmic scales, the other artificially at quantum scales. Both are teaching us about the universe and our place in it. And both remind us that reality is far more interesting, far stranger, and far more wonderful than everyday experience suggests. The coldest place in the known universe is waiting out there, not to be visited, but to be understood. And in understanding it, we understand ourselves a little better too. The coldest place in the known universe connects us to the largest questions about existence. It shows us limits and possibilities. It demonstrates that understanding nature requires both observation and theory, both cosmic perspectives and quantum insights, binding together distant nebulae and laboratory atoms under one elegant framework of physical law. Thank you for joining me on this journey to the coldest place in the known universe. If you found this exploration fascinating, a like or subscribe really helps the channel keep making these deep dives into the cosmos. The Boomerang Nebula sits out there right now, 5,000 light-years away, cooling itself to 1 Kelvin through nothing but physics and stellar death. And in laboratories around the world, scientists are creating even colder temperatures, billionths of a degree from absolute zero, exploring the quantum realm and testing the limits of thermodynamics. Both teach us about the fundamental nature of temperature, energy, and the universe itself. We live in a cosmos full of extremes, from the unimaginable heat of stars to the profound cold of dying nebula and quantum condensates. And understanding these extremes helps us understand everything in between, including ourselves. Good night, and may you never take warmth for granted again.